Hello, my name is Matteo Marulli, and today I'm going to talk to you about my work, DocWaveDiff. Document restoration is an interesting area of image analysis. Many commercial document AI applications use document layout analysis algorithm to analyze document, content, and OCR tools to extract text from documents. Many of these algorithms are trained on clean documents images and work very well on them, but their performance drops dramatically when applied to real-world documents, which are often contaminated by noise, blurring, and scribbles. Therefore, it's important to design image restoration algorithms specifically tailored to the document domain in order to remove noise and preserve and enhance high-frequency information. In this paper, we present DocWaveDiff, an image restoration method designed specifically for the document domain. The key contribution of this work is the integration of wavelet function within diffusion methods based on the predict and refine framework. Wavelet functions are well-known result and come from signal theory. For this work, we used 2D wavelet functions, which are designed to work with images. Wavelet functions are ways to decompose the signal into different parts, highlighting the information content without loss. This function divides the signal by separating low-frequency information from high-frequency information, which in turn are separated into vertical, horizontal, and diagonal frequencies. This function can replace the pooling layers that we can find in many networks, such as the famous U-Net network, and do not require parameters that can be learned to be used, unlike layers such as stride convolution and transport convolution. Hardware are among the most commonly used functions for working with images that have noise and blurring. They are also among the easiest functions to use. In our work, we replaced the classic U-Net of diffusion model with a Wavelet U-Net, where the downsample and upsample layers were replaced by wavelet function and the inverse. Since our model consists of two networks, our goal is to make the two networks work together to achieve hand-to-hand training. The main task of the early predictor networks is to recover most of the low-frequency content of the image, and it is trained with a pixel loss, while the task of recovering high frequencies is entrusted to the diffusion model, which is trained to predict the residual image. This is achieved by minimizing the total training loss as shown in the slide. To evaluate our model, we use two benchmark datasets, the ENS-EXAM dataset for the handwriting removal task and the document blurring dataset for the blurring task. Our model ranked first in the ENS-EXAM dataset challenge. We achieved the best PSNR and increased it by almost 5 points compared to the previous best, the lowest mean square error value ever, and the best multi-scale structural similarity index measure. We have also provided a qualitative assessment of the reconstruction for both the pages and the whole image. As you can see, DocWaveDiff is able to completely remove handwritten text and fill it the white gaps with appropriate content, but it can occasionally be slightly inaccurate in filling these regions. In this slide, you can see the process of removing handwriting from the entire document. As you can see, the model is very accurate in removing handwriting text thanks to the help of the binary mask. On the document blurring dataset, our model outperformed DocRes on both LPIPs and multi-scale the structural similarity index measure metrics. but lose to DocRes by about 1 point on the PSNR matrix. Here too, we have included images to visually show how DocWaveDiff restored blurred images. We evaluated the blurring task in terms of OCR as we mentioned it at the beginning of the presentation. OCR algorithm suffer when the document images is corrupted by noise or blurring. So we measured OCR performance first with the blurred document and then with the restored document. As you can see, there is a big difference. Performance improved, although we can say that the type of CR influenced the performance. Finally, we performed an ablation study. From the ablation study, we discovered that the importance of the various components of the model depends on the task. For example, the presence of binary mask, which helps the model decide which pixel to modify and not, is fundamental, while the use of the attention layer wavelet functions and the diffusion model seems to be negligible details for the task of removing and writing. In the blurring task, removing the attention layer and the wavelet functions leads to lower performance, while it is interesting to see that removing the diffusion model to compute the residual and improving the high frequency leads to 1 point improvement in PSNR measure, but a worsen for the LPIPS metric. To conclude and summarize, our work proposes a restoration method based on the predict and define framework for diffusion model, where the units of diffusion model have been replaced with a wavelet unit. And our model has demonstrated solid performance for the end writing removal task on the ENS exam dataset and a strong deblurring performance on the document deblurring dataset. We also evaluated the model performance in terms of OCR by measuring the performance of OCR engines with the restored documents and saw a clear improvement of OCR performance. Finally, the ablation study revealed that the importance of the part of the models depends mainly on the task. Wavelet functions proved to be very important for the document blurring task, but much less so for handwriting removal task. So I have concluded my presentation. If you have any question for me, you can contact me at the email address here. And thank you for your time and